Hello, I'm Dr. Bettina Heinz, and we will be doing something more in chemistry today. We will discuss the second part of our bonding chapter, the episode 2, and let's see what we have to discuss today. Well, the items listed here are bond order, bond length, bond strength, lone and bonded electron pairs, coordinative bonding, formal charge, resonance, polarity vectors, delta positive and delta negative, designation, and molecular and ionic species. I will begin here with the carbonate ion, which in the Lewis dot structure is given as follows. We have the bonded pairs and the lone pairs, and we see here also different bond order. So bond order means what type of bond, electron shared bond do we have, or how many electron pairs are shared between two atoms. If there are 2 electrons involved, we have a bond order 1, a single bond. If there are 2 electron pairs, or a total of 4 electrons shared, then we have the bond order of 2. If there are 3 electron pairs, or a total of 6 electrons shared between the atoms, we have the bond order of 3. So you see we have here double and single bonds involved. And the lines, remember, are the valence bond lines, which involve shared electrons. And the dots around the atoms, or the atomic symbols, are what we call the lone pairs. Electrons like to pair off. If they are unpaired, they are very reactive and don't rest until they are paired off. So they're called radicals, highly reactive species. So we have here a 2 negative ion, and the location of the bonds can fluctuate. That means we have what we call resonance structures, where the Lewis dot structures can vary a little bit. That means single bonds can become, lone pairs can become bonded pairs, or bonded pairs can become temporarily lone pairs. But that only works actually most of the time with higher bond orders. When we take these 3 possible resonance structures and superimpose them, we have what we call a resonance hybrid. That means the electrons are so delocalized between the individual atoms that you can never really pinpoint them. So they're sort of all between the atoms. Now, why do we have resonance or hybrids? Well, the bond length will change because a double bond is shorter and a single bond is longer. And when one does measurements like X-ray crystallography measurements, one finds that the bonds are all equal, even though according to the Lewis dot structure they shouldn't be. But according to the hybrid, we have equalization of the 2 types of bonds. So it's somewhere in the middle between 120 angstrom and 1.41 angstrom. By the way, 1 angstrom is 0.1 nanometers. By the way, these little dashed lines are used to indicate hybridization of the electron pairs, or spread out or delocalization of the electron pairs. So they are not actually there. They're somewhere floating about this whole structure. So a total number of 3 dashed lines means 6 electrons are rotating about this structure, becoming bonded pairs, becoming lone pairs. So it's an oscillating situation. Remember, the ion or the molecules, they are usually in one type of status quo, but we humans want to get order into things, and that's why we need to separate things so we understand situations better. We don't want a fuzz. We want to separate things out a bit. So the carbonate ion is a trigonal planar ion. So it's completely balanced out. All the bonds make the equal lengths of a equilateral triangle. And here I would like to show you the Lewis dot structure in an enlarged form. And if I'm careful, I'm going to put this whole thing over here so you can see what's on one of the slides. So I have to zoom in. And I hope you see this. So this is my one resonance structure of the carbonate ion. And I quickly want to point out how this works. So if one electron pair moves out and becomes a lone pair, and one electron pair, lone pair moves in to become a bonded pair, then I'm going to make a quick exchange. Then we see a new resonance structure formed, and now the formal charge is going to be here at the other carbon. So this can go around and around, and as we've just seen, carbonate ions have 3 resonance structures, and I will show them to you here in the slides. So here's resonance structure 1. Remember what the formal charge is? Formal charge is what the atom should have minus what it has at that point. So oxygen should have 6 electrons, but has 1, 2, 3, 4, 5, 6, and half of the bonded means 7. So 6 minus 7 is minus 1. That's what we call the formal charge. And here you see the formal charge is shifted to another oxygen by moving a bonded pair out to a lone pair, and a lone pair is moved in and becomes a bonded pair. So here's the third resonance structure, and overall we have the hybrid. So you see the dashed lines represents delocalized electrons. So a total of 6. The total charge is 2 negative, don't forget, it's still an ion, and the bond angles are perfect 120 degrees. And all the bonds are in between a double and a single bond. Here we have another example of a molecule, the Lewis dot structure of a molecule. So only focus now on the slides. And we see here that is formaldehyde, the formaldehyde molecule with the carbon in the middle, and the oxygen, double bonded oxygen, with the 2 lone pairs and 2 hydrogens attached. This is a very important molecule that is formaldehyde, or formalin, makes formalin solutions, prevents decay of organic tissue or biological tissue. Now we can, with the arrow formalism, point out that one of the electron pairs is going to move out and become a lone pair. This now leads to the next form, which shows the formal charges that are a result of this process, because carbon now has no more 4 electrons surrounding it, but only 3, half of the bonded pairs. So remember, should have minus half, 4 electrons minus 3. So now we have a positive formal charge. The oxygen here, being the more electronegative element, will get the negative formal charge. So that's a resonance structure of the formaldehyde molecule. And you see the dashed green line represents that that's a fluctuating electron pair that oscillates between being a bonded pair and a lone pair. And here we have the delta plus and delta minus designation, which derives from the electronegativity difference of the atoms involved that make this bond. We also have the polarity vector here, the arrow with a little plus sign at the end. That's used for chemistry polarity to designate or show in which direction the polar bond is leading to. So the negative end of this bond is the oxygen. The positive end is the carbon. Delta comes from the Greek alphabet. It's the little d, meaning differential of a charge. That means the electron density is shifted in direction of oxygen. The more electronegative element gets the bulk of the electron density. It's unequal sharing. So we have also 2.4 is carbon, and oxygen is 3.5, very electronegative element. The difference will indicate how strong that polarity is in that particular bond, which happens to be a double bond. Here we have another resonance structure of another ion. This time the ion is nitrite, NO2 negative. Formaldehyde was a neutral molecule, so the formal charges have to balance to 0. But when we have an ion, the formal charges balance to whatever electrostatic charge that ion has. So let's see, you can already guess what the other resonance structure will be. One of the lone pairs will go in and become the second part of the double bond. That means the bonded pair. And on the left side, the bonded pair will move out and become a lone pair. So you can already guess that the negative charge will hop on to the other oxygen. And here we have it. So that's the second resonance structure. So there are two resonance structures. A resonance means the ion or the molecule is stabilized. So the more resonance structures are possible, the more stable that species is. And we call this whole process delocalization. And here would be the hybrid. That means when you take one resonance structure and the other and superimpose them, then we have sort of this in-between situation. So the two dashed lines represent a total of oscillating 4 electrons. And the whole charge is somewhere in between then. The determination of the overall polarity has to be in such a way, performed in such a way that every bond receives a polarity vector, and then you have to just do a computation by combining these vectors and getting so-called resultants, and in the end you get one resultant vector, and that will be then the overall polarity of the molecule. Sometimes the vectors can cancel each other out, like in carbon dioxide we have a vector going to one high oxygen from the carbon and another vector pulling with equal strength to the other side, and then we have a net vector direction of 0. So the overall polarity of carbon dioxide would be 0. However, carbon monoxide is not balanced out, so it still has a residual vector going in a certain direction. And the resultant vector, which we can see here in a trichloromethane or chloroform, each carbon chlorine bond is very polarized, and if you take all the vectors and compute them to get a resultant vector, you have almost like a lampshade with a string pulling down, and that means the overall dipole is from the hydrogen going in between the 3 carbons, 3 chlorines, because it's a tetrahedral structure. And here we see how we work this. Like water is an angular molecule, we have one vector going from hydrogen to oxygen and the other vector going from the other hydrogen to the oxygen. And when you combine them, you get a resultant vector that is in direction of the oxygen. So in the end, you want to have one dipole, one remaining dipole. And a dipole means 2 poles connected. So plus and a minus connected, like a baton. And we see here the hypochlorous acid is also polarized in the direction of the oxygen, oxygen being stronger than chlorine. And here we see what I just talked about, the carbon dioxide with a net thrust or net polarity of 0, and carbon monoxide having the vector in direction of the more electronegative element. So we learned a lot about resonance, which are in a way superimposed Lewis dot structures, or we can also say that they are electronic isomers. Okay, here we go. I don't want to get into this too much because we have already talked about these situations. So we can say again that the more resonance structures we have, the more stabilization is achieved, and we call the whole process resonance stabilization. Here we see the SO2 molecule that also has 2 resonance states. Since it's a molecule, the total number of formal charges have to balance to 0 because it's a neutral species. The resonant hybrid is here in between, fluctuating back and forth, back and forth, back and forth. So actually it's sort of right in between the 2 oxygen arms. Here we have some other molecules, such as nitrous oxide, laughing gas that makes you laugh when you visit the dentist. And we have the nitrite ion that we already discussed, and here we have the formate ion coming from formic acid, which is the acid that the ants use to repel their enemies. So the hybrid structure always uses the dotted lines. Hybrid means a mixed bag. And we have already talked about the delocalization. Delocalization means that the bonds are never really fixed. The main framework is constant, but you never know where your children are at the moment. So the electrons are always migrating to different atoms, and that's what we call delocalization, as already pointed out. And we have seen in the other model the different carbonate ions, so this would be repeating what I already showed you earlier. Informal charge, don't forget, is always what the atom is born with, how many electrons it brings in to the game, and what it ends up with. So it's lone pairs and half of the bonded pairs. So the oxygen in these cases is always, when it doesn't have a double bond, what it should have is 6, and it has 7, so it's -1. Here on the bottom, we see the phosphate ion. The phosphate can have many resonance positions, so it's a very stable ion. And all the formal charges add up to 3 negative, as we can see here in the image. Now, we already talked about bond order, right? And we know what it means. Bond order means that we are dealing with covalent bonds, and we have bond order 1, 2, and 3. Apparently not 4, although at times we can find C2 molecules. That means diatomic carbon molecules in very high energy states, which give off a blue flame usually. When you heat a gas stove and you see blue flames, then it's mostly based on C2 coming from the gas that you use for combustion. So 4 shared electron pairs is highly unusual, but maybe in extreme energy states, such as with the C2 molecule, it's possible. But for ordinary times, we have a single bond with 1 electron pair shared, a double bond with 2 electron pairs shared, and a triple bond with 3 electron pairs shared. And we see it here in our slide. Hydrogen would make a single bond. Oxygen would arrange itself with another oxygen into a double bond, and nitrogen will produce a triple bond with its neighbor, which is another nitrogen atom. So these are the diatomic gases, some of them, and you see they all want an octet, with the exception of hydrogen, of course, because it cannot make any more. So the duet is the one that hydrogen wants to achieve, the helium electron configuration. But oxygen wants an octet, and nitrogen wants an octet, and they get the octet. So the idea is to get the octet no matter how we bond with each other. So you see, when we look at the formaldehyde, molecule again, we see a double bond and two single bonds. And hydrogen or hydrocyanic acid or hydrogen cyanide has one single and a triple. And when I ask you how many lone pairs, then you can say yes, one. And formaldehyde has two lone pairs and a total of 4 bonded pairs, and HCN has 4 bonded pairs and 1 lone pair. Now let's look at some numbers and compare bond length, bond order, and strength of the bond. We can roughly say that a single bond is longer than a double, which is longer than a triple. A triple bond brings the atoms closer together. It's just like having more rubber bands, so to speak, to hold the atoms together. So the bond shortens with bond order. The strength also increases with bond order. A triple bond holds better than a double bond, and a double bond holds better than a single bond. The bond strength is usually measured in kilojoules per mole, which is energy per mole. And here we have some values given. The green values here show the relative bond strengths. And let's look at the triple bond. One of the strongest bonds is the nitrogen-nitrogen triple bond. That's why it's so difficult to get nitrogen out of the atmosphere to make important nitrogen compounds that are usable for life on Earth. So that's why nature developed enzyme systems like nitrogenase, which uses a molybdenum cofactor or central metal ion that is able to, with some other metals like iron and protein components, to literally separate that strong bond of the two nitrogens. Another very strong bond is carbon monoxide. It's 1,070 kilojoules, and the two nitrogens is 946 kilojoules. The carbon-carbon triple bond is 837. And if you compare it to the double bond strength, it's 611, and the single bond strength is 346. So you could say that it's not quite a multiplication effect, so doubling effect. So 346 times 2 would be more than the double bond, and 3 times this would also be more than the corresponding triple bond. So there's no linear relationship here. But we can say definitely the trend is that the more bonds are involved, the more stable, and the shorter the length is. And we also see here that the nitrogen-nitrogen triple bond is 0.109 nanometers, and the single bond is 0.140 nanometers. Good. Let's leave this behind for a moment. But everything is related, so things reoccur in our discussion. And one very important bond is what we call the coordinative bond. Remember, we learned in bonding 1 the ionic and the covalent bonds, and the coordinative bond is sort of in between. They call it sometimes the mixed double bond. And when you look here, let's say we have A with a lone pair and B that would be an electron acceptor that has nothing but wants to bond with A. Then A says to B, let me give you one of my electrons, and then we can pretend we're doing a covalent bond. However, when that happens, automatically formal charges have to be produced, because the A, by giving away one electron, sort of becomes positive, and the B, by accepting an electron as a gift, becomes negative. So you see when they make their pair bond, then we still have to include the formal charges. Sometimes we can say that a coordinative bond is like a piggy bank type of bonding, like B sees that nice lone pair and just settles on it like a backpack to that A part of the atom that we consider A. So the bonded electron pair is only provided by one of the bonding partners, and the other atom, in a sense, borrows an electron that it can use again to make a bond. And this always is related to the development of formal charges. And here we can understand why it's sort of considered a mixed double bond. In the old days, they used to call it a mixed double bond, because we have a real bond, right? The real electron pair bond. But with the formal charges, it's sort of like an over, or it's surrounded also by a quasi-ionic bond because of the opposite formal charges. So you can say it's sort of a covalent bond with an overlapping ionic type of bond. They used to call it also a dative bond, having nothing to do with dating, and it was expressed usually by an arrow. So if you see old literature or old chemistry books, an arrow sort of pointed in the direction in which the coordinative bond went. And here we have sort of a human situation of coordinative bonding. The man says, I'm rich and you are poor. Let's make a bond. Let's get married. And here we have another example of a molecule that was hydrocyanic acid, which has a lone pair, as we learned before, and an oxygen just settled on it. Now we also have some unusual species, like odd electron bonded species. These are called radicals, and these electrons are sort of passed back and forth between the species. And we also have exceptions to the octet rule, which can be a sextet or an expansion to a dodecad. Thank you very much.